Hey everybody, this is Larry. Today we're going to go over monoqueues. Hit the like button, hit the subscribe button, and leave a comment on any questions and join the Discord and join everything. So what is a monoqueue? Monoqueue is short for monotonic queue, and I actually really much dislike the name because the name monoqueue describes a property of the queue. Like it tells you what it is, but like how do you use it? Why do you use it? Why is it important that it's monotonic? And it probably, to be honest, for me, I feel like it actually doesn't really matter that much that is monotonic. And we're going to try to solve a couple problems toward it. The way that I would like to think about it, about both monoqueues and the two versions, or there are more versions, but more two common versions, which is a monotonically increasing queue and a monotonically decreasing queue. I prefer to call it mono max queue or mono min queue. I actually prefer to call it max queue or min queue, but sometimes that gets confused with a heap or a priority queue with a max heap or min heap. Anyway, it's very easy to get confused with the terminology, and I think it doesn't really matter that much with respect to the naming. If you know what it is, like it doesn't matter if you know the name of things. It matters what you know about these things, right? So today we're going to work on solving a couple of problems that uses these monoqueue problems and how I will attack these problems and how I did attack these problems during the contest. So, it's not just me like, this is not a perfect video of, hey, you should have already known this. It's me kind of thinking through my thought process as well. Okay, so before we jump into what a monoqueue is, I want to describe the abstract data type that we want to implement to solve a lot of our competitive programming problems or interview problems. And in this case, right now, at this point, it doesn't matter what the implementation is and it doesn't matter what the complexity is. We just want to define the things that we want to implement, right? So now, let's say we call it min-q for, and I call it min-q, I prefer to call it min-q because it describes the data type. Like instead of describing a property of the queue, it describes the problem that we're trying to solve with this queue. And here we have an enqueue function, which just puts a value into a queue. Let's leave these as a skeleton for now. You have a dequeue function, which removes the beginning of the queue. Remove an item at the beginning of the queue, first in, first out kind of way, like a normal queue. And a getMin function, which returns the minimum element inside that queue. And right now, the complexity doesn't matter yet because we just want to be able to solve problems, and the implementation of this min queue will determine the complexity of our algorithm, obviously. But we just want to be able to solve it in general without worrying about the complexity, and this is how we're going to do it. And in this problem, let's jump into this problem with what we have of abstract data type. 1438, longest continuous subarray with absolute difference less than or equal to limit. Given an array integers nums and an integer limit, return the size of the longest continuous subarray such that the absolute difference between any two elements is less than or equal to limit. In case there are no subarrays satisfying the given condition, return 0. Okay, so what are we doing here? Okay, so the problem is saying that, first of all, how many subarrays are there? We're looking at n. In this case, n is 10 to the fifth, which is 100,000. You have other limits on the number, but essentially, it's saying that n squared is not fast enough. But before that, and there are n squared subarrays. So now we're trying to figure out, well, what is this problem asking, right? And can you do like a sweep line, scan line algorithm from left to right? Yeah, and we can use a sort of a two-pointer sliding window type algorithm. And the sliding window, which you have to do some research on your own if you have done that. But with the sliding window, we want to figure out, in general, well, we have an invariant that we want to keep, and that as we slide our left fingers and the right fingers, or left and right pointers, that this invariant, we have a way to make it true and that it stays true for that happening, right? And when that invariant is true, we can just take the max of those. For this problem, we can take the max of the longest subarray because the invariant will always be true and always contains all the subarrays. There's a part about greedy that you have to prove on yourself. I want to focus on the monoqueue part. But the idea is that, okay, let's take a slightly bigger array for an example. Let's say we have an array like this array. This array. You have a left pointer and you have a right pointer, and you want to just move the left and the right. And what do you want to get the left and what happens within this span, right? Let's move this a little bit to the right. So within this segment or span between these two indices, we want for this problem to contain the absolute difference that is less than or equal to limit, right? And how do you get the absolute difference between the max and the min element, right? Well, I guess maybe I jumped ahead a little bit, which is that the absolute difference between the greatest absolute difference between two elements is basically you have a function that you have to convert a little bit. You have basically you want basically the max of ij. Well, you want to loop over the max of ij such that a sub I minus a sub j, the absolute value, is less than or equal to limit, right? So that's kind of the problem with asking. And now you can make the reduction that just means max of a sub a from I to j. The notation's a little sketchy, but stay with me. To the min element from a from I to j, is less than or equal to limit, right? So given that, and what we said about sliding windows, as we move to, so what happens when you move to the right pointer, right? Well, when you move the right pointer, you add 7. In this case, you add the new index into the into whatever segment that you're adding, and then you want to, if it's no longer true, you want to also remove to the left pointer. Oops. You also want to move the left pointer to, and when you move your left pointer, you also remove 10 in this case, right? So as it turns out, and well, we have the max and the min, but as it turns out, that fits this abstract data type perfectly, right? As something that we need. Basically, we have, this is a little bit off by 1e, because you just want to be able to enqueue, which means add a number to the right, or the right pointer number, and you want to be able to dequeue, remove the left number, and you want to be able to get min and max in this case for this problem. So let's also write out the abstract data type for the max queue. And we'll leave it here for now. And now we can start, writing this sliding windows algorithm. So now we have something like, I write my sliding windows a little bit my way. Feel free to write it your own way. But yeah, I start with the left and the right at 0, and then while right is less than n, let's define n is the length of the list. Also, I always try to increment at the end. I know that this is like a for loop, but for me, it's easier to add variations to this. So that's the way I usually do it. So what happens when you add a number on the right, right? So on every loop, so now let's say we have a min q. Is equal to min q, max q is equal to max q. And now, using these abstract data types to solve the problem, we have min q. I write a pen because it isn't more Pythonic, maybe. But now we want to enqueue num sub right and max q as well, right? And then now, well, once we add in a number, we want to check the max and the min. I think I have typo. Once you enqueue the number, well, what we have to check whether our invariant, or we have to keep our invariant true, right? So now we just do a check. If max q dot get max minus min q dot get min is greater than or equal to, or greater than only, right? Yeah. And this should be a while loop because we want to actually keep doing it until that case is true. Because if this is too big, then this invariant of keeping it under limit is no longer true, right? So now, if that's the case, we do a pop or a DQ from the front. Yeah, and that's pretty much it. Well, we have to do some, that's pretty much it for the min max queue. And now we have to figure out the size, right? So this is where kind of the left is handy. So in this case, we actually don't need to do this explicitly because the abstract data type will do it for us. But you could imagine us doing it another way. But here we just move to left plus 1 because we dequeue one element from the left, right? And then now the invariant after this while loop to fix it, the invariant that everything inside your segment will hold that the max element minus the min element is less than or equal to limit, right? So now the max minus min element is less than / equal to limit. Now we can calculate the size of this queue. And the size of this queue in this case is just right minus left plus 1, I think. Could be off by 1, but we could check that easily. And we start with a queue of 0, and that's all there is to this problem conceptually by itself. Obviously, we still have to implement these. Okay, so now we want to figure out what the complexity of this algorithm is, keeping in mind that this is still not implemented yet. So the complexity of this algorithm is, well, look at each element in the numbers list. We only enqueue once for each, well, okay, twice, but constant amount of times. So 2 enqueues per element on the numbers list, and 2 dequeues on every number on the elements list. And for each, because we only loop this n times, this at most we will only do a couple of times for each element. So we have a constant amount of dequeue and unqueue operations for each element. So that means that this is O of n times the cost of enqueuing plus n times the cost of dequeuing plus the cost of n times the cost of max and min. So that's roughly right about right. So now your question might be, well, what are the costs of these things? Right now we want to spell out what that is. So the complexity right now, let's summarize a little bit, is we have n elements, and for each element we enqueue at most once. Well, actually exactly once, right? At exactly once. We dequeue exactly once because, well, if you only enqueue once, then you can only dequeue once. So our complexity is O of n times the cost of enqueue plus cost of dequeue, right? So that's kind of our complexity right now. And let's say we do a very naive algorithm. Let's say we, oh, I forgot to write the constructor. For both of these. But yeah, let's say we use a very naive algorithm, right? Let's say for min q, we do something like, yeah, self.q is equal to just, and yeah, and or actually we want to use, in Python, we want to use something called the collections.dex, so we could remove from the front. And a deck is a sort of a more general version of a queue. So now in queue, we just want to do enqueue sub.queue dot, I think append dot, well, dq sub.queue dot pop left get min. So how do you do get min naively, right? Well, get min we could do naively by just looping through the queue, right? For x in sub.queue, let's just say min is, oops, or smallest is equal to some infinite number. And then now the smallest is equal to the min element. Or actually, yeah, you could just, in Python, you can actually just do this, right? Just get the smallest element. And then now let's think about what these complexity would be, right? And you could do the same for the max cube, but for now we'll hand wave it. Okay, so what is the total complexity, right? So right now we only factor the cost of the NQ and the DQ, plus is actually this plus total cost of get max, get min, right? And what is the second part? Well, the second part is just you could analyze this, the number of get max, get min costs times the cost of each individual get max, get min cost, which I think still should be okay to follow for now. And the second part we're saying that we'll figure out later, but the number of get max, get min costs, right? Well, for every DQ, we call this once. Well, we call each of these once. And for every NQ, we also call these ones, right? So because each element gets NQ and DQ'd once at most, as we talked about earlier, each of those calls get max and get min once. In total, there are 2n number of calls to get max and 2n number of calls to get min. And so we can actually just rewrite this as 2n times the cost, something like that, right? And also you could, just hide it in the forward band. So this is basically the total cost, right, of the algorithm. And you could now combine them to the cost of each individual get max, get min cost. Right? Cool. And now, given this formula of how to analyze this complexity, well, what is the complexity of NQ? That's all of 1. That's just a standard deck Q complexity. What's the complexity of DQ? And DQ, also all of 1, right? Because this is just a deck, and that is also pretty standard. Getting the min of the queue, the entire queue, we just go through the entire array, which will take all of n times. So together now we can see that this is all of 1, this is all of 1, but this is all of n, which dominates the cost of this function, which makes it n squared. So the question is, can you do better? Well, yeah, you can take advantage of the fact that you're enqueuing one element at a time and dequeuing one element at a time. And there are a lot of data structures that actually do this for you. Really introductory one is the binary search tree, a balanced binary search tree. Well, let's say that we have a balanced binary search tree by itself. Well, how would you use that binary search tree, right? And in Python, it's a little more complicated, and we'll go over it as well. But let's use a binary search tree. Let's say we have a magic binary search tree API. Well, what are some binary search tree operations? At this time, we'll remember the constructor. And then you have a insert value and a removal. So maybe there's some trickiness to it. And then maybe get min or get max. Both generally doesn't really matter. Or they have the same complexity, right? So now let's say we have a abstract out type of binary search tree, a balanced binary search tree to be clear. just to clear that up a little bit. Then how we would use it? Well, on enqueue, we just do self.value. Yeah, let's just keep this short so I write a little bit. We insert the value. On dequeue, we remove the value. I guess that is terrible naming. Hang on. Because these should be actions. And then the get min in this case would just be, well, not get min, right? Oh, whoops. You can tell it's live because I make silly mistakes. Okay, so now, well, what are the costs of these operations, right? Well, if you remember your balanced binary search tree days, insertion will be O of log n, remove will be also O of log n, and get min is also O of log n. There are many different types of binary search trees, so I don't want to get into that in this video, but just know that these will be log n, and this will be log n, and this will also be the log n. This is the most critical part, and technically, this might not be in a lot of binary search tree APIs per se. You can just think of it as a way to, given a binary search tree, just keep on going, the leftmost element, and that will be your min element. And you could do that in log n times where n is the size of the tree because log n is the depth of the tree, right? So that would be how you implement this. Now you have gotten a new complexity to analyze. What is the complexity of this algorithm now? Well, the cost of enqueue is log n, cost of dequeue is log n, and the cost of each individual get max, get min costs are all log n as well. So now, with BBST backed, we have n log n algorithm. You go done. GG, well played, right? Well, almost. I have a typo here. So we remove a value without actually, it's just like a magical thing. But actually, we want to get the value that we're removing, and we could make this slightly more clearer by doing something like this, getting the top of the queue. And yeah, we should gate it for making sure that it has more than 0 items and stuff like this. But so now we get the value, and then now we remove the value. So that's how you would do dequeue. And now, if you're using a language that has a balanced binary search tree implementation of some sort, then you're done, right? With C++ or Java even, I think, sets are implemented by balanced binary search trees. So then you can just plug and play, and then you're pretty much done. I'm in Python, and I know that there's a sorted list or something like that, but I am not familiar with it, and I need to be more familiar with it. So I'm going to show a technique that I did during a contest recently. I end up using heap or a priority queue. And the way that I was thinking about it was that it reminded me of the Dijkstra's algorithm, where you may insert stuff, but you delay dequeuing of things until later. So that was part 1 of the Monoqueue tutorial. Hit the like button, hit the subscribe button, wait out for part 2 later on coming soon. Join the Discord, join the algorithmist link, and let me know what you think. Bye-bye.